All right, what do we do? Substitutions and homogeneous and Bernoulli's equation. So let's get started with substitution. That is looking for an appropriate substitution. In some cases, they could give us a substitution. In some cases, you will have to figure it out. All right? So, okay, so again, just like in when evaluating integrals, you would look for a pattern u to u, so you can figure out what's the best choice of u, So that's what we're doing somehow when solving these differential equations. Right? Now, here's the thing. Look at that differential equation. It's not a linear equation. It's neither separable because, well, look at the cosine contains both variables y and x, the dependent, and so that makes it a nonlinear differential equation. All right. However, in this case, they're being really nice, and they are giving us the proposed substitution. All right. Okay. So from here, what we do, let's solve for y. Y equals to vx squared. All right. So that's going to be our. From here, we're going to differentiate, okay? So, because in this case, all of them, v, y, and x, they all depend on x. When we do the product rule for this, we need to use the chain rule somehow, all right? So, let's find dy dx. dy dx equals to v, which is a function of x, which we don't know. Well, that's going to be, let's call it dv dx times x squared plus the derivative of x squared, which is 2x times v. Okay, so that's the product rule in action here, along with a chain rule and implicit as well, because we don't know what that v is. All right, but we know this v depends on x. All right, what's the purpose of all this? The purpose of all this is to replace, all this dy dx over here, and whatever we substituted for v, and that's gonna give us a nicer equation to work with. Okay, so what does that become? So number one, dy dx, which is all this madness here. That's 2. Let me go dv dx. Times, okay, let me go x squared dv dx plus 2xv, okay? And that equals 2y over x. So 2y over x, but I'm going to substitute this y right here. So 2 times y, which is vx squared divided by x, plus cosine of v, all right? Plus cosine of v. Okay. So actually, a lot is going to get reduced because number one, check. So we can reduce 1 power of x. Okay, that leaves us with x squared dv dx. Okay, dv dx plus 2xv equals 2vx, or simply 2xv as well, plus cosine of v. Okay, and check this out. These two go away. Okay. And what do we get? This equation reduces nicely to x squared dv dx equals to cosine of v. All right? And look at that. Doesn't that look like a separable equation? So from a non-linear equation, a very crazy-looking equation, it became separable after doing some magic here and there, right? Well, not magic, an appropriate substitution, Okay, so, well, let's separate the variables. I'm going to multiply both sides by dx, so that's x squared dv equals cosine of v dx. Okay, let me make this v look like an actual v. Okay, sometimes my v's can look like x's. If there's something unclear, let me know. All right, but I'll try my best to write the v's correctly. Okay, so this will be, by separating variables, dv over cosine v equals dx over x squared We're almost there to integrate. We can't integrate the cosine in the denominator. However, how about secant, right? Secant v equals, secant v dv equals x to the negative 2 dx. And guess what? Integrate. What's the integral of secant? ln of secant plus tangent, right? Secant v plus tangent equals to, is that x to the negative 1 over negative 1 plus c. Again, we only add the plus c on the right hand side of the differential equation, of the solution to the dE, right? Okay, so although, well, actually we're not, in some cases we may not be required to express our solution in, in explicit form, because notice how many functions have the dependent variable, so we wouldn't be able to solve it in this case. However, we can still get rid of the natural log. For the one on the take-home quiz, you will be able to do everything, like get rid of the ln and solve explicitly. You'll see. Okay, so let me fix some powers right here that it's the same. Negative 1 over x plus c, okay, secant v plus tangent v ln. Well, let's get rid of the ln by exponentiating. Okay. Now again, this is the same. Secant v plus tangent v. Okay. Absolute value of that. That is equal to e to the negative 1 over x times e to the c, right? But what is e to the c? E to a number we don't know what it is. Well, you can call it another constant, or just keep using the same c. It doesn't matter, really. It doesn't matter. All right, so let's do that. And at the same time, I will, c e to the negative 1 over x. I'm going to back substitute for what we got for v. Okay, what did we get for v at the beginning? Y over x squared. So that'll be secant of y over x squared plus tangent of y over x squared. All right, and that is our general solution. And yes, no, don't even try. Oh, I forgot the absolute value bars, right? In this case, in some cases, I could get rid of these absolute value bars. However, we don't have an additional condition next to the equation, so that for such values, we can simply skip them. All right? Anyway, so that's one example. We do a substitution. In some cases, we're given such substitution. In some other cases, we have to figure it out. I believe that's what the next exercise is about. All right? Okay. Example number 2. They're asking us to solve the equation dy dx equals to y plus x raised to the second power by making an appropriate substitution. Yes. The way we are going to come up with the appropriate substitution is in a similar way as if you were evaluating an integral. It's typically whatever is inside a radical, whatever is inside parentheses, whatever is inside in the exponent of an exponential, or in the argument of a logarithmic function, you name it. All right? The difference is we're going to have a function. We may have an expression containing more than one variable as opposed to evaluating integrals, in which we usually say u equals one variable function, right? Not the case right here. Okay, so any ideas what would be our appropriate substitution?
X plus y.
X plus y, right? So this guy right here. So let's let v equals to y plus x, okay? I'm going to solve for y right here, All right, I'm going to solve for y for a reason. So y equals v minus x, and that's because I would like to take the derivative to also perform a substitution for the derivative term. So the substitution is not only for whatever is inside the parentheses, also has to work for the derivative term in the equation. So right here, take the derivative, dy dx equals, well, v is a function that depends on x. We don't know what it is, so dv dx, dv, not y, dv dx, minus the derivative of x, which is minus 1, right? I mean, if you want to do dx over dx, well, what's dx over dx? Well, that's 1, all right? Okay, with that in mind, okay, let me do another highlight here. So this is what we are going to substitute in the place of dy dx. All right, that's why we'd rather solve for the y, do the calculus on the y, of course, keeping in mind the chain rule with implicit and all that. All right. Okay, let's go. Let's go. So dy dx, which is dv dx equals, wait. No, we were good. dv dx minus 1, okay? And that equals to this quantity, which we said it was v, quantity squared. All right? Let's see. What can we do about this equation? Any ideas how to solve this differential equation?
Arc 10, like moving the minus 1 plus 1 and then doing the...
So separating the variables, right? So at first glance it doesn't seem separable, right? Because of the terms like all over the place. So if we solve for dv dx, this is equal to v squared plus 1, and dv over v squared plus 1 equals to dx, and we can easily integrate this one, right? And yes, the first one, it's a pretty basic case of an arctangent function. That's arctan of v. And guys, unless you have something like 16v squared plus 64, just make sure to use to consider the a and the u du part, all right? This one is a very straightforward one, and equal to x plus 1. All right? Okay, so, well, at this point you can do either the solving for v or the back substitution. Doesn't really matter. I'm going to do the back substitution. Arctan of y plus x equals to x plus 1. And in this case, we can solve explicitly for y, right? We can take the tangent on both sides and also subtract the 1, all right? So, take the tangent on both sides. That's going to cancel tangent with tangent, and with arctangent, I mean, and that's y plus x equals to tangent of x plus 1, where y equals to tangent of x plus 1 minus x. Oh, hold on. I think I forgot a c right here, right? I don't know why I add the plus 1. This plus 1 right here should have been a plus c. Now, I don't know where I get the 1 from. I think I was looking at the 1 right here. I don't know. All right? That's supposed to be a plus c. Okay? Yeah, I'm going to annotate those on the YouTube video, so yeah. Okay. So, well, those are a couple of examples when, well, in some cases a substitution is provided for us, or in some cases we have to come up with the appropriate substitution. Now, there is a very special case of a substitution for a very special type of equation called a homogeneous differential equation. All right? However, before getting into solving different homogeneous differential equations, we need to discuss what a homogeneous function is. So let's have a look at this definition here. So, a function of two variables or three variables, or how many variables you want, but for our purpose, only two variables, is said to be homogeneous of degree n if f of r of x or f of rx comma ry equals to r to some power n times f of xy for some real number r, whatever that is. All right. So we will figure that out. Okay. How do we know if a function is homogeneous? Well, so let's have a look at these two variable function. F of xy equals to 2x to the 6 plus minus 4y to the 6 plus 7x cubed y cubed. Okay. All right. Well, so we will replace every instance of x with rx and every instance of y with ry. That is 2 times r to the rx to the 6th power minus 4 times ry to the 6th power plus 7 times rx to the 3rd ry to the 3rd. And let's simplify all this. Well, we'll have to basically use laws of exponents. That's all it takes, really. So this will be equal to 2r to the 6 x to the 6 minus 4 r to the 6 y to the 6 plus 7 r cubed x cubed another r cubed y cubed. All right, a bunch of powers, a lot of terms and a bunch of powers. Well, let's kind of simplify this a little. Well, the first two terms, just leave them the way they are. All right, so that is 2 times r to the 6 x to the 6 minus 4 r to the 6 y to the 6, and what's next? Okay, 7, so plus 7. Okay, the only thing we can do for the very last term is to multiply the r cubed with the other r cubed, giving us an r to the 6, x to the 6, oh wait, x to the 3rd, y to the 3rd. Okay, one thing to notice here to get out of this, it's, do you see the r to the 6 to the as a common factor? Factor it out. That's r to the 6 times 2x to the 6 minus 4y to the 6 plus 7x cubed y cubed. All right? Well, in this case, does the quantity inside of the parentheses look exactly equal to the original function? It does, right? So this is the same as saying r to the 6 f of x y. Well, with this, we say, yes, homogeneous of degree 6. Okay? This is a homogeneous function of degree 6. Not all functions are homogeneous. For instance, consider, let me give you another example at the top of this exercise, like f of x y equals to x squared plus x cubed, for instance. All right? Yeah, I should have typed that example to show you an example of what it is homogeneous and an example of what it is not homogeneous. Okay, if we substitute, well, let me do f of r, well, let me do it here, f of rx, ry, that would have been rx squared plus rx cubed. In a similar way, laws of exponents, distribute each factor, okay? That is r squared plus r cubed x cubed. All right? Okay, let's factor out r squared. However, do you guys notice we can't factor all powers of r? So we can only factor r squared, leaving us with x squared plus rx cubed. Now, look at the quantity inside of the parentheses. Does that look exactly like the original function? Almost, except because of that extra power of r. So no, this is not homogeneous, right? So how can we tell by just eyeballing a function? Okay, power 2, power 3, overall power 2, overall power 3. Well, different overall powers for every single term. The example number 3 we did here, Overall power 6 for the first term, overall power 6 for the first term, and well, for this product of variables, what do we have? Power 3 and power 3. Both add up to the same variables, to the same power 6, right? So, by just looking at the function, you can tell it is homogeneous of degree 6. The minute this is maybe a 2 right here and a 4, for instance, right there, it's no longer homogeneous. Some powers of r are going to be left when trying to factor it out. All right? Okay. Now here's the thing. Now let's get into the homogeneous differential equation. Okay, so a differential equation of the form m, which is a function of x and y times the differential x, plus n, another function of x and y times the differential dy, equals to 0. Is said to be a homogeneous differential equation. However, be careful, if both m and n are homogeneous equations, or functions rather, but they have to be the same degree for both. Otherwise, the method is not going to work. Alright? So, now here are the steps to solve such a kind of equation. So, number 1, perform the substitution y equals to vx. And of course, find the differential of y using the product rule x dv plus v dx. All right, we're using the product rule for a differential of a product. So we're going to substitute number 1, this guy for y in our equation, and this guy for dy in our equation. And then, well, that's going to do a lot of, at first it's going to look a big mess, by the way. However, then it's going to turn into a really nicer equation. You'll see. Okay? So, and then we'll rearrange the equation algebraically to obtain a separable equation. So what are we going to do? So we are going to work with a crazy looking equation. We're going to do the substitution to turn it into a separable equation. But because in this case we will be working on another domain, a domain x and v, we need to undo what we have for v by back substituting v equals to y over x. Alright, well, I guess let's have a look at a couple of exercises to see this in action, of course. Okay, so number 1. For example number 4, we're given a differential equation. So showed, number 1, letter A, showed that the D is homogeneous. Okay? Well, so I think by looking at whatever is multiplying the dy and whatever is multiplying the dx, we can tell it is homogeneous. Both functions are homogeneous of the same degree. Because what's the degree of 2x? Isn't that degree 1? That's going to output an r to the first. And then, yes, you have 2 terms. However, degree 1 plus degree 1, it's still another degree 1. All right? So, well, first, let's show this formally. Okay, let me rewrite the equation first in the form. So that's negative x plus y dx plus 2x dy equals to 0. Okay, so m equals negative x plus y, and n equals 2x. All right? So that is negative rx plus ry. That equals, factor out the r, negative r, x plus y, which is negative r times, in this case, it's m. All right? To the first power. Homogeneous of degree of degree 1. All right? Number 2, 2x. Okay, so this is the same as saying 2 times rx, but wait, this is 2rx, which at the same time this is r times 2x. Isn't that again? Okay, no, this is still first. Okay, this is r to the first power times n, which is also homogeneous of degree 1. So that takes into account for both. So that means we can solve this differential equation using this method of homogeneous. All right? Okay. So number one, let me go back to the substitutions very quickly. Okay, yes. So y, okay, so to solve the equation, we will use the substitutions y equals to vx. Then dy equals, what is that? V dx plus x dv. All right? How are we going to do this? Okay, let me highlight. Highlighting is going to help us because here, for this method, there's going to be a lot going on initially. So y equals to vx. Okay, let me highlight. Okay, that's only one y, right? It's only one y. What about the dy? So dy with another color. Let me use green for this. Okay, and let me substitute that into here. Okay, actually I should have used the solved equation. Okay, over there. All right. Okay. Substitute, and well, for a vast portion of the problem is going to be a lot of algebra. All right, it's going to be a lot of algebra. Okay. So this will be, let's see what it is. Oh, yes. Okay, so negative x plus y, which we said it's vx, okay? And that times dx equals to, what was that? 2x times dy, which is all this, wait, it's plus, right? 2x times, careful, parentheses, v dx plus x dv, and let that be equal to 0. All right? So let me again color code the highlightings here so you can see where is everything coming from. All right? Okay. So, well, the rest of the problem, a little bit of algebra here and there, okay? And, well, a bunch of terms usually get canceled to leave us with a somewhat nicer and easier separable equation. Well, so be careful over here because I'm going to distribute the negative and also the differential dx. So that's going to leave us with negative x dx and then minus vx dx also. And then, okay, so here I distributed the negative and then the dx as well. I'm going to distribute the 2x over the two terms inside of the parentheses. That is 2x or 2vx dx plus and plus 2x squared equal or 2x squared dv. All right? And let that be equal to 0. All right? Okay, can we cancel any terms here? Well, I mean, like, canceling terms, not really. However, it seems like we could combine some of the like terms, right? So this will be, okay, negative x dx, and then these two terms, right? The vx dx, 2 minus 1. Let me use a different color to show you which terms are we canceling or combining, really. This term with that term. 2 minus 1 equals to 1. That's simply plus vx dx plus 2x squared dv equals to 0. Okay, so at this point, how do we continue working with this equation? I mean, we have a bunch of dx and dv's. It doesn't look like any of the equations we have solved before. However, as we said in the definition, this equation will be eventually a separable one. All right? So for a separable equation, we leave everything containing the dependent variable, which at this stage of the problem, because of the substitution, the dependent variable is v. The independent variable remains x. Okay? So, this means 2x dv, or 2x squared dv, equals to, I'm going to move, okay, x dx minus, or did I, oh, that's supposed to be a minus 2. Oh, no, that's a plus. Plus, or minus rather, yes, minus vx dx, all right? It seems like we can factor this out, all right? We can factor x and dx, okay? So this will be 2x squared dv equals to, okay, let me factor dx first, x minus vx. I don't want to do the two factorings in one shot, so you don't freak out about it. So I'm factoring dx first. And do you guys agree we can also factor the x? That's x times 1 minus v dx equals to 2x squared dv. And we're almost there, right? We're almost there separating the variables, because have a look at this. Okay, x dx, it's already on the right hand side. We only need to move the the 2x squared, and also we would need to divide both sides by 1 minus v. Let me do one at a time. Okay, let me do one at a time. Okay, let me use a different color for this. Okay, so I'm going to divide both sides by 2x squared. And this will leave us with dv equals to x divided by 2x squared. That's 1 minus v dx over 2x, all right? And, well, I don't want to make this quotient look weird. I'm going to multiply both sides by 1 over 1 minus v instead, okay? Rather than dividing by 1 minus v to make it look like a 3 fraction, I don't like that, all right? So this will be dv divided by 1 minus v equals to, what is that? Dx over 2x, all right? Well, number one, before integrating both sides, any ideas how to evaluate the integral on the left-hand side? What would be a good idea here? ln, right? However, I don't want to show the u du, so I'm going to factor the negative, the v, and then v minus 1. It will be easier, right? And then this is 1/2 integral dx over x. Okay, so actually ln rule on both sides, right? So that is negative ln of v minus 1 equals 1/2 ln of x plus c. Okay? Can we... Yes. Okay, so I'm going to multiply both sides by negative. Okay, yes, because I would like to solve for v. ln of v minus 1 equals to negative 1/2 ln of x plus c. And finally, let's exponentiate both sides. All right. So, okay, yes, number one, we could eliminate e with ln right here, but we can't do it on the right-hand side because of the coefficient negative 1/2, right? Basketball, the coefficient first. That's going to leave us with v minus 1 equals to e to the ln of x to the negative 1/2 and the negative 1/2 plus c. Oh, okay. How about instead times e to the c again, all right? Which by absorption will be another coefficient in front of the exponential here. So number 1, e with ln finally cancel out, leaving us with x to the negative 1/2. But again, what is this e to the c? Isn't that just times c? And this is absolute value of v minus 1, which, well, I don't want to do the plus minus because the plus minus is going to get absorbed by the c on the right hand side, right? So that's why at this point I can simply v minus 1 cx to the negative 1/2 and keep going. What is that? V equals to cx to the negative 1/2 plus 1. So that's only the solution to the differential equation within the world of the substitution. So we need to go back, substitute. Okay, how do we go back, substitute? Well, let me go back to the definition we had at the top, in the previous page. Well, so we did y equals to vx. So we have a function that depends on v. So if we solve this, y equals to vx, so v equals to y over x, which is how we're going to back substitute to go back to the world of xy, not to the world of xv. Okay? So just to get rid of that independent, or rather intermediate variable, okay? So but y equals vx means v equals to y over x, okay? So y over x equals to cx to the negative 1/2 plus 1. All right? And what is this? Y equals to x times cx to the negative 1/2 plus 1. And in this case, you might want to distribute the x. Okay, so this is x to the first power, right? First power minus 1/2, isn't that equal to cx to the positive 1/2? And x times 1, that equals to x, which you can interchange with, what is that? C square root of x plus x. Final answer. Final answer. I wonder if oh no, never mind. So I thought I did a sign mistake. No, I don't think so. Yeah. Okay. So that was one homogeneous equation. I believe there is another example right here. Oh shoot, I should have. Don't think I brought the notes for. Okay, I'll have to improvise on this one. I thought I brought my notes for that one. Okay. Solve x minus y ln y plus y ln x dx plus x ln y minus ln x dy equals to 0. Well, that looks like a huge equation, and yes, I'm not gonna lie. So the way this equation is given, we first need to do a little bit of work before getting it done. All right? Well, in particular, okay, first things first. Look at this group right here. Look at this group of terms right here. All right? So, how about factor out the y? Well, actually, I'm going to factor out negative y because I'd rather have the following. Check. So, I'm going to use brackets, by the way, to avoid confusion with too many parentheses. That is x minus y times, how about ln of y? That'll be, factor. If I factor negative, I would have to go, plus ln of y minus ln x. All right? Do you guys agree with this? And also, x ln.
The sign on the outside.
Yes. So negative ln of y, and then negative times the negative then becomes a positive for ln x after distributing again, right?
The one next to the y?
The one next to the y right here. Yeah, this is the one that has to be negative. Or we can just factor out the y first and then the negative sign. All right? Because the negative times a positive, that becomes a negative again, this one. And then negative times a negative, it's positive, this one, right? Yeah, that's kind of a weird factorization. And then here I'm going to use quotient rule of logarithms. ln of y over x. Okay? dy. Oh, wait, no, that's a plus. And then equal to 0. Okay, in a similar way, I'm going to use properties of logarithms to x minus y, ln of y over x. Okay? This dx plus x ln of y over x dy equals to 0. Okay? Alright, now, so what do we have? We have an equation of the form, okay, m dx plus n dy. Alright? Okay, so we need to check whether each function that multiplies the dx and the dy are homogeneous, and specifically whether they are homogeneous of the same degree for both of them. Alright? Okay, what's the degree of x right here? Degree 1? Do you guys agree it's degree 1? What about degree 1 right here? What about ln of y over x? Okay, check. How do we, because ln, it's not polynomial, so, however, ln of ry over rx, what happens? Ln of simply y over x. So that doesn't affect, in this case, it doesn't affect if it's homogeneous or not. However, if, okay, let me do a what if at the top. If you had something like ln of y squared over x, okay, this would be ln of r, or r squared, y squared over rx, which would be, ln of ry squared over x, and that's no longer the original function, right? So that particular factor or term, depending on how it is, wouldn't be homogeneous, all right? So, but in this case, it is for this one. Okay, what about this one? Degree 1, okay? Did you see the degree 1 right here, the coefficient of ln? What about y over x? Okay, another cancellation, so both homogeneous. Of degree of degree 1. All right? So, okay. So, okay, that means we can already set the substitution. What was that? V equals to, no, y. What was that? Y equals to Vx. And dy equals to v dx plus x dv. All right? v dx plus x dv. Okay. Let's get to substitute this. All right. Again, let me highlight using the same colors as before. Okay. Y equals to Vx. Substitute into every single y in the differential equation. And the dy, there's only one place for dy, right? That'll be dy over here. All right. Take a deep breath because lots going on here. Okay. All right, let's see. So x minus y, which is Vx, ln of y, which is Vx, over x. All this multiplying dx, and for dx, we don't do any substitution. All right? What about the second term? Plus x, which is just x, ln of another y equals to Vx over x. And here, multiply by v dx plus x dv. However, because this dy contains two terms, make sure to put parentheses around it. So this X ln x of all this madness here is going to be distributed later to the two terms, all right? Okay, so what do we do next? Okay, so how about eliminate these x's, and let's see. That's x minus vx ln v, all this dx, okay? And plus x ln v again times v dx plus x dv. Okay. Let's see what's going on. Okay, so number one, I would like to distribute the dx with the x and with all this term. And this x ln v right here with x dx. All right? Distribute, 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 distribute. So 4 distributions here. All right. So x dx minus vx ln v dx plus xv, which is vx, isn't it? Vx ln v dx. Oh, aren't those going to cancel? Right? And, forgot the equal to 0. Don't forget the equal to 0. And x squared plus x squared d plus x squared ln v dv equals to 0. Don't forget the equal 0. I forgot in the previous couple of steps. All right? Okay, whatever we can cancel, yes, do. Okay? This will help us go with the equation in a nicer way. So what do we get? Okay, x dx plus x squared ln of v dv. And we'll look at the equation. It turned into a nicer separable equation, right? So that big term containing the dv, leave it there. Move the x dx to the right-hand side. That is x squared ln v. Okay, let me make this look like a v, correct? dv equals to negative x dx. All right? Okay, so that's dividing both sides by x squared. That's ln of v dv equals to 1 over x dx, but don't forget the negative on the right-hand side. All right? Okay, we have our variables separated because, again, for a homogeneous equation, once we do the substitutions, we do all the algebra and all that, we have to end up with a separable equation. Guys, if for whatever reason you don't get a result like this, I mean a separable equation, double check your substitution, all the algebra in between, or maybe that equation, they told you it was supposed to be homogeneous, maybe it's not homogeneous, you know, so double check, all right? Double check. Okay, well in this case it is. We can already integrate both sides, okay? The integral of, that's going to be negative ln x plus c on the right-hand side. However, what about the left-hand side of the equation? Integration by parts, right? Integration by parts. So let me do the integration by parts on the side. Let me use a different color for that. Okay, so maybe, yeah, this color. Okay, so the integral of ln of v equals, oh, shoot. Okay, here is a problem. So because we're using the letter v because of, what is that? Because of the differential equation. However, the problem here is for integration by parts, we are also going to need a v, right? So guys, just turn this into ln of x dx, okay? So just so you don't get oh shit, we're also using oops, this is going to YouTube's. Anyway, I mean there's channels that are anyway. Yeah, but this is okay. Anyway, so all right, so yeah, so u equals to ln x, right? du equals to 1 over x dx. That means dv equals dx, or v equals to x. All right? So that's u times v, that's x ln x, minus the integral of v, which is x, du, which is 1 over x dx. Let me continue down here. So this is equal to x ln x minus, boom, cancel out, integral of dx equals x ln x minus x plus c. Well, actually, we don't need the plus c for the left-hand side, right? And well, because we're just using this intermediate variable x just for the side trip, let me also box the side trip with a different color so you don't get confused. All right. So this will be v ln of v minus v, all right, equals to negative x ln of x. And guys, don't even try. This is not, we can't solve for v in this case, right? We can't. So simply back substitute for v, all right? So v equals, y equals, come on, y equals vx. This means v equals y over x, all right? And that gets substituted into every instance of v in our solution. That is y over x ln of y over x minus y over x equals negative ln of x plus c. And this is okay to leave it in implicit.